to oxygen, and X-ray grazing incidence. For neutron, I find 10 nanometer thickness of the oxide on a niobium film, high pressure rinsed on sapphire. And by X-ray, I find 3 nanometer. And this is the same wafer cut, from different pieces. So I guess it depends very much on the technique you are using when you want to calculate the thickness of the oxide. I know XPS show more or less 3 to 5 nanometer too. So this is still a mystery. But it might be that the thickness is thicker than actually what we think it is. So basically all this to say that a factor of 10 is easily achievable between that atomically flat 5 nanometer thickness to the real volume of the oxide, which would mean then it's come only from the oxide. And this is magnetic impurities in the oxides, which correlate with what I showed you before. And if you estimate a concentration, you have roughly 1%, whereas the point contact show more or less 0.1%. So we have, but this is somehow normal. This is measuring the whole volume. Point contact is measuring the effect of magnetic impurities, which actually, the superconductors feel magnetic impurities which are the closest to itself, which means it has to be not in the insulating outside too far from it, but right on the interface. So basically we will have less impurities felt by the superconductors than there is really, factor of 10 roughly. And this is Raman spectroscopy that we did on BCP foils here, for instance, and we see strange structures where the Raman intensity signal increased a lot in this supposing, here labeled as rough spot with respect to the smooth spot in blue here. And this is the same on pits in niobium cavities. This is, for instance, a pit, and all this has been done at IIT. When you go across the peak, the intensity of the Raman signal increases a lot and then decreases back in point D here. So there is, and this intensity enhancement is attributed to amorphous oxides. So this again leads to an enhanced volume of the oxide as what we estimated. So now this is just a summary of the experimental result. I think there is more to do, of course, but we have pretty good evidence that there is magnetism. So now the point is, how do this influence the dissipation? Well, we did a small theory at Argonne, calculating the surface impedance, the real part of this, this term, in the London limit, supposing an homogeneous repartition of magnetic moments. This is easier than rather the inhomogeneous model where you have just a layer of magnetic impurities, which is closer to reality, but this is just easier to do. And in the dirty limit, dirty limit is, let's say dirty limit. We have 3 parameters, and I will come back to it a little bit later to explain each of them. The mean free path, normal mean free path, so diffusion on normal impurities, non-magnetic. And we have eta and alpha, which are 2 parameters describing the effect of magnetic impurities on the superconductor. So we have 2 types of impurities here. So we compute self-consistently the Shiba equation and the gap equation, and from the F and G value, which is, anomalous and normal green functions, then we can compute the normal electron density of state and the superconducting electron density of states. All of this goes into the surface impedance here. Yes, and also you can compute the, so this have only these parameters. This gives you the gap, this gives you TC, this gives you lambda, this gives you everything else. But what is eta and alpha? So how does this affect? So in the Shiba theory, this is what would be a perfect superconductor without any magnetic impurities. 0, 0, a sharp quasi-particle peaks, and going back to the merging into the normal state at higher energies. In the Shiba theory, you have delocalized state that start to appear inside the gap at an energy given by eta. Alpha is basically the concentration of magnetic impurities. When you increase alpha, you increase the concentration for a fixed eta. What it has an effect to broaden these peaks and to lower these peaks too. So now, for this set of parameters, if we plot the value of the zero bias conductance, which is here, as a function of the temperature, so the temperature is increasing along this line, and we plot this in the same way as people plot Rs versus 1 over T, we have this line here like that. So it's almost like BCS for high values of eta. However, if we decrease slightly the value of eta closer to the Fermi level, and we increase, but we don't have to increase, but increase slightly alpha, so this is larger, you see, as compared to the previous peak, then you start to see a saturation when you decrease in temperature, which reminds strongly of the residual resistance. So, okay. This is a computation of the surface impedance versus the mean free path. But we will focus, this is not true. So the calculation we thought were true for all mean free paths, but Alex kindly reminded us that actually this is not true in this region. We forgot a term which is always non-local in the NN, basically. So we will just focus on the left part of this graph, left from this minimum, which is mean free path smaller than psi. In dot line, this is a true dirty limit. In thick line, this is what we thought was the arbitrary mean free path limit, but this is valid here on this left part. This is not valid on the right part. So we'll just concentrate on this part. But we are, from this thick line, we see that we are, and we will reach a minimum. Whether the hard part is slightly shallower has been seen also in BCS. Matisse and Bardeen have seen it for BCS theory. So now we are redoing all the calculations, summing over the whole impurity later, which is kind of a long process to do. But within a month we will have a correct theory for all mean free paths, or left and right side. So now we can fit the surface impedance versus 1 over T. This is data given by Gigi. So what they did is, this is a baseline in black always, and the red is after baking at X temperature, and here it is 120, 180, 90, 160. And it fits pretty well. And we can extract some parameters, concentration of magnetic impurities in dot in the squares here versus baking temperature, and delta over KTC on this scale here, which is around squares, versus temperature. So in black is before baking, so the baseline. In red is after baking. We can see that delta over KTC increase after baking. That was found also when fitting the with BCS theory. And the concentration of magnetics seems to be increasing pretty monotonically with the baking. The higher you bake, more or less the more magnetic impurities you have. But it's between typically 100 ppm, sorry, not percent, and 200 ppm. We can also plot the mean free path and lambda as a function of the temperature. So here, this is not correct because this is on the right part of this minimum. So I would, but it's just to say that on the previous graph, there is two values of the surface resistance that give equally good fits for two different mean free paths, one on the clean limit, one on the dirty limit side. So we don't know exactly what is the clean limit side, but we know what is the dirty limit side values. So this is why these points are high in the clean limit side, but we don't know how high they are exactly. However, on the dirty limit side, we know. So this is a mean free path, and this is in square versus the baking temperature. And here you have a point where it's split. Basically, you have the choice. Or you take the dirty, or you take the clean limit side. So in blue, this is the dirty limit side, and it will look like that, with a peak at 120C. So the highest mean free path, if we consider only the dirty limit side solution, would be at 120C. If we consider both of them, and once again, these values are not exact. They are much higher than these blue values, but they are not exact. We would have a minimum. And what we noticed is that at this point, 120C, it corresponds exactly to the minimum, I mean, really close to the minimum on the dirty limit side of the surface impedance versus mean free path. So it looks to us that actually it's a combination of both. We go from the clean to the dirty as we bake more and more. And correspondingly, in dot curve, lambda increase, going to the dirty limit. We find also that after baking, the mean free path is always reduced, and lambda is always increased. We can estimate a value of the concentration, which is 250 ppm. So this is much less than what I thought before, but this is because it's diluted onto lambda and not just onto few nanometers at the surface. So a more exact model will have to be calculated, which could take into account the inhomogeneous repartition of magnetic impurities, not homogeneous. So this can be seen 250 ppm as an average concentration. That if you would concentrate it onto 1 nanometer, you should have the same thing, and we do. So this is future work. As Alex mentioned in his talk yesterday, we send samples, so it's niobium films, this resonator in the middle, with different surface treatment to try to see if magnetic impurities could affect this nonlinear Meissner effect. And we did some SQUID measurement on each of this type of sample we send them. So there is a bunch of them here, but this is in black. It's 60 nanometer film niobium coated in situ with tungsten, so no oxides, TC of 9 Kelvin. The 30 nanometer is the blue one, so it's thinner, also coated with tungsten, so no oxide. You can see a small bump here. It's probably the proximity effect of the tungsten. And then you have 60 nanometer of niobium with water, and this is a blue curve here, with also a bump, which tends to think that there is a dead layer on the surface or slightly reduced TC. And the 60 nanometer is this purple one, with also a reduced TC here. And you have air, what we have also done just with air. So the niobium films never saw water. And then we will see how this affects the nonlinear Meissner effect. And that's it. Thank you.